the Diels-Alder reaction. This is one of my favorite reactions. It works really well in the lab. It's really predictable. We tend to have really good control over both regiochemistry and stereochemistry. And it's also a reaction that forms new carbon-carbon bonds. So this means that for synthetic chemists, this is a really useful reaction. So what we've got written down here are the two partners that come together in a Diels-Alder reaction. So we have a conjugated diene, and we have another molecule that has a pi bond, and this will love to react with the diene, so we call this the dienophile. And so a few things to note here about the diene and the dienophile. The first thing you might notice is that this is not typically how we would draw this diene. We're used to seeing zigzag structures like this. And indeed, this diene can adopt this conformation, what we typically see where things are more spread out and less sterically hindered. And we could also say that these alkenes are pointing in opposite directions. So we would call this conformation the S-trans conformation. And so although this conformation exists, it's not the conformation that reacts. But as long as your diene is able to rotate, and we have a single bond in the center of this molecule, so that is freely rotating. So as long as your diene is able to rotate and get into this reactive S-cis conformation, then it can undergo a Diels-Alder reaction. So that is one requirement of our diene, is that it must be able to adopt the S-cis conformation. And that's really the big restriction on our diene. And then if we look at what we are reacting it with, the dienophile, it just needs to be a molecule that has at least one pi bond. One carbon-carbon pi bond. So what I've drawn here is just a simple alkene. It could also be an alkyne. So our dienophile could be an alkene, and it could be an alkyne. All right, so what happens in this reaction? So what we have is we've got 4 carbon atoms of the diene, 2 carbon atoms of the dienophile. I've left these unsubstituted. You will see many examples with lots of things dangling off of all of those carbons. But the reaction takes place with just these 6 carbon atoms, which is why I've only drawn them. So what I'm going to do is I'm going to number the diene. 1, 2, 3, 4. Those are the 4 carbon atoms of the diene that we're going to keep an eye on. And 5 and 6 on the dienophile. And here's what happens in a Diels-Alder reaction. So it is a cycloaddition reaction, so although I'm going to start my arrow here, I could actually start it anywhere because I'm going around in a circle. So it doesn't matter. So what I'm indicating here is that I'm forming a new bond between carbon 6 and 1. That's going to shift this pi bond down to be between carbons 2 and 3, and we will push this pi bond out. And so what we are forming here is new sigma bonds, or single bonds, between carbons 1 and 6, and 4 and 5, and the pi bond, I'm only going to have one pi bond left from these arrows, and that will be between carbons 2 and 3. So I'm going to draw a 6-membered ring, and I have a pi bond between carbons 2 and 3, and so I'm going to number this. 1, 2, 3, 4, 5, 6. And that's it for the mechanism. That's all that happens in this reaction. And so any substituents that were attached to carbons 1, 2, 3, 4, 5, or 6 would simply still be there in the product. And a few other things to note, this is a concerted mechanism. And so that means that if our dienophile happened to be an alkene that has stereochemistry, if it was specifically a cis or a trans alkene, we would see that stereochemistry would be retained in the product. So if the alkene has stereochemistry, it will be retained. Okay, so let's just look at a quick example over here and throw in something with some stereochemistry and see how we can apply this rule. So I am going to draw a diene, and I'm going to throw some substituents on there, throw a methoxy group on there, and let's look at a dienophile. And so let's say we have this dienophile. And so what I did is I put an electron donating group on my diene, and I put some withdrawing groups on the dienophile. So what that does is make one partner nucleophilic and one partner electrophilic, which is required for a reaction to happen. Okay, and so I am going to number 1, 2, 3, 4, 5, and 6, because these 6 carbon atoms are all I need to keep my eye on in this reaction. Everything else basically comes along for the ride. If it was attached to a carbon, it's still going to be attached to that carbon in the product. So 1, 2, 3, 4, 5, and 6. And so if I'm drawing a product, I could draw the reaction arrows if I wanted to. I'm not going to bother. I know what's happening. I'm just going to draw this cyclohexene. Because no matter what, every Diels-Alder reaction will give you at a core a cyclohexene. And so 2 and 3, those carbons is where the pi bond is. So I always start labeling there. It's easy to see it. And then I'm just going to keep numbering around the ring. So 4, 5, 6, and 1. Okay. And then to complete this product, I just want to make sure that any substituents that are attached to this carbon haven't fallen off along the way. So if I look at my diene, the only substituent is at carbon 2. It's that methoxy group. So I will put the methoxy group at carbon 2. And then if I look at carbons 5 and 6, I have these aldehyde groups, and I see that one is pointing in this direction and one is pointing in the other direction. So this was a trans-alkene to start with. So because this reaction takes place in one step, we say the alkene stereochemistry will be retained. So what does that mean for the product? It means that we're going to have one aldehyde pointing in one direction and the other one pointing in the other direction. In other words, we're going to put one of these groups on a dash bond and the other one on a wedge bond. So there's one, and I put that facing into the plane of the page, so I will put the other one sticking out of the plane of the page. And so you might be wondering, well, how did I know which one went where? Well, you actually get both possibilities. There's nothing that's going to make this top one go back and this one stick out. So if we wanted to be really complete, we would also draw the product where the top bond is sticking out of the plane of the page and the other one is going back into the plane of the page. And you might recognize that these are enantiomers of each other. And so don't worry about that. What I'm going to be looking for you to do is just to show me one of these, either one, and let me know that you recognize that that stereochemistry has been retained.